Okay, this is Mr. Roki. This is the remainder of Chapter 3. We're talking sections F, G, and H. We're going to start off by talking about exponential graphs. This is the general form of an exponential function right here. There's a lot going on there. 4 different variables for us to worry about. Let's dive in, shall we? First of all, we're deciding that b has to be a positive number. There's a very important reason for that. B can't be negative because if it was, if I had b negative and I had my x value equaling, for example, 1/2, then I'd be taking the square root of a negative number. And so that's just not going to be defined. If you try to graph something that has a b value that's negative, you're going to get something weird like this. Hey, wait a second. I said that wouldn't work. Of course it doesn't work. We got to follow order of operations here, folks. This is not negative 3 to the x. This is actually 3 to the x and then made negative. This is what happens if we have a negative b value. So you can kind of see like there's little dots that are actually shown where the function would have a value, but in most cases it's not because negative value, we just can't raise it to so many powers. So we're not going to consider these, although it's an interesting kind of thing. It kind of goes up and down and up and down and up and then very down, and then it's actually going to go even farther up and then even farther down, but it's just not connected, so it's not something that will be studied. All right, so b is going to control how steep the graph increases or decreases, so that could be like 2 to the x, and this might be 3 to the x, for example. A larger value is going to have a more steep increase. C is going to control horizontal translation. So remember what we saw with vertex form of a parabola, and I also discussed modulus functions earlier. So if that were to say x minus 2, then our graph is going to move 2 units to the right. And if it were to say x plus 11, our graph would move 11 units to the left. So there's that repeated structure again that we keep on seeing, all right? Eventually, I want you to just be comfortable with the fact that there really is only one set of rules controlling how functions operate. So you don't need to memorize a different set for every different type of function. It's a lot easier than a lot of people think that it is. So anyway, likewise, D controls the vertical translation, right? So just like with vertex form of a parabola, that would be, we saw it as the letter K in that case. That's shifting the graph up and down. D also happens to be the value where the horizontal asymptote is going to be for each of these. So they all have a horizontal asymptote either below or above. And then the A and the B value kind of work together to determine what the overall shape of the graph is. In general, I'm going to say that whenever the B value is greater than 1, we're going to see exponential growth. So both of these on the left are growing. The one on top is growing in the positive direction. The one on the bottom is growing in the negative direction. Positive, negative. And these two on the right, these are called decay. This is going to be positive exponential decay. It's decaying, so it's getting lower. And this will be negative exponential decay. To use some words from later on in the course, once we start studying some calculus, whenever a is greater than 0, our graphs are going to be concave up. And whenever a is less than 0, our graphs are going to be concave down. One final thought, you can kind of think about parabolas, I guess, in a sense. When the a value in a parabola is negative, we have a parabola that opens downward, and that's what we have if we imagine those two pieces. They're both opening downward. Whereas when our a value is positive, we have something that's opening upward, and that's what those two would be doing if we put them together. All right, so when we sketch exponential functions, we definitely need to have the horizontal asymptote labeled. We definitely need to have the y-intercept labeled. And then the book suggests that we have at least 2 other points. I don't know if that's necessarily super important. I mean, the more points you have, the better. But having 2 other points is not really going to be an official rule for us. Certainly the y-intercept and the asymptote, however. One more word that I want to say about these before we move on is just to be on the lookout for other ways that these functions could be written out. So for example, if I had a function that said y equals 7 times 1/2 to the x, that's the same as 7 times 2 to the negative x, right? So this b value here could be bigger than 1, but this function is still going to have this shape because now it's no longer to the power of x. Now it's to the power of negative x. So if you're going to try to memorize these shapes, make sure that you really pay attention to the fact that this x has to be positive for these 4 shapes to actually match up with the rules as written. And later on, when we get to chapter 5, we're going to see that when we change a function from a positive x to a negative x, the result of that is always going to be a horizontal flip. And you can see how this graph, if flipped horizontally, would lead you to this graph. So again, just a little preview of future ideas. We always want to stop and reflect to think about how things we've learned tie together with things that we've seen in the past. Hopefully that'll be a little bit easier if I start to prompt you to think about them once we get to them. Anyway, let's try to graph a few of these here. We'll just do 2 of these. We'll do one with growth and one with decay. All right, so we'll start with letter A. Looks pretty simple. I know from the get-go that it should have this basic shape because my A value is +1 and the X is also positive X. So it's going to be just standard exponential growth. But let's get a more specific graph going here. The domain and range. For every exponential function, our domain is always going to be that x is a real number. They're always going to be defined for every x value. For the range, our range is always going to be y is either greater than or less than a number, and that number is going to be our horizontal asymptote, which in this case is 1. It's going to have to be y is greater than 1. When we don't see a number there, the horizontal asymptote is just the x-axis, so it would have been y is greater than 0 in that case. So there's our domain and range. I don't know, this is totally arbitrary. It wants to know what happens when x is equal to the square root of 2. So if you grab a calculator, you're going to get 3.67 in this case. As I said, totally arbitrary number, not of any interest whatsoever. Discuss the behavior of y as x goes towards positive infinity, negative infinity. As x goes towards positive infinity, y is also going to go towards positive infinity. Clearly, as x gets really, really big, 2 to the power of x gets super, super big as well. As x goes towards negative infinity, well, as x is a super, super, super big negative number, then I have 2 to a negative power, which means we're really just going to have 1 over 2 to that really big number, which means we're really getting 0 out of this first term. 0 plus 1 is 1. It's approaching 1 from above. So that's how to algebraically justify that the asymptote is definitely 1 and that my range should be y is greater than 1, because I can tell just by thinking about what happens with the x value here that the y value has to be getting closer and closer to 1, but from above. And the horizontal asymptotes, okay, we've already worked that out. The horizontal asymptote is y is equal to 1. So for my graph for this, I've got my axes. There's my line. Label it y equals 1. Oh, I should probably work out what the y-intercept is. They didn't ask me for that. The y-intercept, when x is equal to 0, I'm going to have 1 plus 1, which is 2. So we'll put that there. I think this is a great picture. If you want to include the square root of 2 point, we can say that that's there, I guess. But again, I don't know why you would want that. But anyway, that's a great sketch of this one. Let's do one more. I want to do letter D this time. And before I work out anything, I want to, again, just kind of think about what should this graph look like from the beginning. If my normal exponential graph has this shape, well, what's happening here? I notice that there's a negative in front of my b value, so that means that my graph is going to be flipped upside down. But then I also notice that the x is negative. So I discussed what that is going to do earlier. That means that it's going to be a horizontal flip. So I should have this shape. The domain and range. The domain is still going to be all real numbers. The range in this case will be y is less than 3. 3 is going to be my horizontal asymptote. In this case, if you're interested, when x is equal to the square root of 2, y is equal to 2.62, whatever. The behavior as x goes to plus and minus infinity. As x gets really, really big in the positive direction, we are going to have 3 minus 2 divided by a super, super big number. That's 3 minus 0. So I'm going to say y approaches 3, and it's going to approach it from below, because it's always going to be something just less than 3. It's 3 minus something that's almost 0. And as x goes to negative infinity, then I'm going to have 3 minus 2 to the power of infinity. That's a super, super, super big number. 3 is not even going to register on this. We're just going to have y is going towards negative infinity as well. And that end behavior certainly matches the picture that I predicted earlier. So my graph, my asymptote's going to go in at 3. My y-intercept, when x is equal to 0, I have 3 minus 1, which is 2. And this will look like this. Now this one has an x-intercept, and usually we should work out what that is. Unfortunately, without using logarithms, we are not going to be able to solve what is 3 minus 2 to the negative x equals 0. In fact, even with a logarithm, you're not going to be able to get a decimal answer from this unless you happen to grab a calculator, which I did. So if I want to find the x-intercept, I will analyze the graph and find the 0. Okay, so it's negative 1.58. So we could label that on the graph next, and that would be a great picture. Okay, before we get into this, I just want to say we are very unlikely to actually see word problems like this in our course, but it's worth us thinking about at this stage in the game, I think. So this problem is about bears. In fact, it's actually about pairs of bears. We got to read this very carefully. So there were 6 pairs of bears, or 12 bears in total, introduced in 1998, and the population is supposed to increase according to this function right here. And they don't actually specify the unit here, but we're going to say that that's time in years since the introduction in 1998. So b sub 0. B sub 0 is just the amount of bears at the very beginning. That's 12. Again, that's 12 bears, not pairs of bears. The expected bear population in 2018. 2018, well, what's t going to be in that case? Well, that's going to be 20, right? Because we're 20 years into the future. So we're really asking, what is b sub 20? And b sub 20, if you just throw a 20 in there for t, you are going to get rounded to 3 significant figures, 146 bears. Please check my work. Finally, for part C, finding the expected percentage increase. Percentage increase is going to be the amount at the end minus the amount at the beginning divided by the amount at the beginning. So that is going to be for us b sub 20 minus b sub 10, all divided by b sub 10. Again, pump those in. Check my work, please. We should come up with a 248% increase. Now, they didn't ask us to graph anything here, but of course we could have. If we're going to do that, we need to use the variable x. We can't be inputting t into the calculator. It won't know what to do with that. We can't really see anything here, so just because I don't think I've mentioned it before, We could just zoom out here, but I would rather go change the window settings just to get a good look at this. So X is representing time. I'm not really interested in what happened in the past before 1998 because that doesn't really make any sense in my problem. So I would start at t equals 0. And this could go, I don't know, let's look 25 years into the future. Why not? Y value, this is going to be my number of bears. That can't go below 0. And I don't know, I'm sure it won't grow too much higher than 250 or so. Let's see. All right, yeah, there we go. This is a pretty good guess. So there's a general idea of what this function is going to look like. It's exponential growth, which I suppose we should have known going into it. Anyway, let's look at one more. So here, the half-life, radioactive substances decaying over time. So this is a classic use for exponential decay, obviously. So let's do this. So first, we're gonna find the initial weight of the substance. So that's again when t is equal to 0. So that's clearly going to be 1,000 times 1. So it's going to be 1,000 grams. My weight after 10 years. So then we're just going to put 10 in for t. That's going to end up being 812 grams. So we can see that the weight is going down over time. After 100 years, we're at 125. And after 1,000 years, we are at the minuscule 9.31 times 10 to the negative 7th. So that's very, very little. Clearly, this is approaching 0 as time marches on. They ask us to graph this. It says using A and B only. In other words, just using the information that we have so far. So without any technology, I know that when x is 0, y should be 1,000. And it's exponentially decaying. And I can just plot the other 3 points if I wanted to. This is 10, 812. Somewhere way out here is going to be 100. And 125. And somewhere way out here is going to be, I don't know, we'll skip a little. And we can have 1,000. And part D, we'll definitely need a calculator for. We want to know when there's going to be only 10 grams left. And I can tell it should be someplace in between 100 and 1,000 years. Of course, that doesn't really narrow it down too much. If we graph this, of course, we actually can't see anything. And I have already graphed. You can see here I've got my exponential function, and I've also got the line y equals 10. The line y equals 10 is just a horizontal line, and it's above the screen, and my exponential function is also way above the screen right now. So let's change the window. My x max can be 0. My x min can be 0. My x max, well, it's not going to be more than 1,000, so let's start there. My y min can't be less than 0. My y max, let's start it at 1,000 since that was my initial weight. There we go. Okay, and way, way, way down here, it's actually tough to tell in this picture. Let me get some stuff out of the way. You can almost see, if you look really closely, that the pink function, the horizontal line, is right down there. So they actually do intersect someplace around right here. So let's get that spot. Find the intersection. Oh, it's right there. Okay, I was hiding behind the function name. So it's going to be at around 221 years. Cool. So the amount that has decayed should be the original amount minus the amount that that is remaining, right? So we can say that the original we know is 1,000. And the amount that is remaining is defined here as W sub t. That's not quite good enough, so I think we should rewrite this as 1,000 minus 1,000 times 2 to the negative 0.03 t. And that's good enough for me. If you want to factor out the 1,000, be my guest, although it's definitely unnecessary. And that brings us to section H, the natural exponential e to the x. So hopefully you've heard about this number e. If you haven't, it is quite a special number. I'm not going to go off on that now, but you can check the links down in the description for some fun e videos. If you thought that pi was a special number to mathematicians, pi's got nothing on e, let me tell you.
Max, you really hate the number pi.
So other than e just being an irrational number like pi, other than that, there's nothing else new in this section. It's just a new base for exponents. Nothing really to worry about. Um, no new conceptual material. That's it for chapter 3. Chapter 4 is linked intricately to this, so get ready to start that right away. Logarithms are just the inverses of exponentials. So if you get chapter 3, you should be fine with chapter 4. Catch you later.